Hi, Busi. Hello.
Hello, sir. How are you?
Great yourself.
I'm good, thanks, sir.
Great. Let's just wait 3 minutes and then we'll begin. Otherwise, how's your preparation going?
Hey, I'm trying, sir, but I'm struggling,
Hmm.
especially module the one with the bonding moment,
Yeah.
module 5. Yo,
Hmm.
uh,
Did you watch the recordings and so on? Did it help you?
I watched the recordings, but hey, I don't know. Sometimes I think I get it, and
Yes.
then I where I lose it. Yeah.
I think you must just share the link. Do you have the link there? I don't know where the link is.
Which one? Your link.
Yeah, my one.
Your one. Let me check here.
But yeah, no, I do understand you. It can be like that on your
Mm,
five. Yeah.
sure.
It comes with practice though. It's doable.
I even took leave, say so much.
Ah,
I leave from work, but still.
what's next? You're gonna call the church 3 hours. What is next?
Um,
Where's this
in
link?
in terms of what? Say?
No, I'm joking, man. I'm saying like you taking leave and now you're gonna be calling the church.
Oh, ish. Yeah, I even
Interesting. Yes.
even to other recordings of the other lectures, but
Hmm.
hey, I
What?
I module 5.
Hmm. Yeah, I think I found the link. I'm hoping next semester or trimester, I'm gonna maybe have class on campus as well, but we'll see.
I hope by that time I'll be done with strength.
Yeah,
I'll be doing strength 6.
yeah. That's another tough one, that one. Um, let's see. It's Cleo. Just go to where is this thing now? Okay. All right, we'll begin. Um, Good evening, Cleo. We'll begin. I don't know who else is gonna join, but yeah. So I'm assuming you guys can see my screen, eh?
Yes, sir.
Perfect. Okay. So before I begin, I'm just gonna quickly go through something. I'm assuming you went over at least you have an understanding what buckling is about. But I'll just place this image here now. And here's my image. Here we go. So here we have just some real so what I'm looking for. Cases where buckling has presented itself. Um just talking to the image, what buckling is, or in this chapter is called column and struts, it is inherent for anything which is a column, which is a strut, which is under compression. It can fail in two ways. Or yeah, the one way it's going to be compressed fully or where it buckles. In fact, buckling is a form of stability. So each column, if you ever design one, right, it is one of the considerations you absolutely must take into consideration. So like, even though this pillar or column over here hasn't broken, it is buckled, right? And this buckling occurs at a load less than the yield. Was it before the yield? Here in this case, we have reinforced concrete, and we have the rebars buckling. So yeah, it's a very common thing what happens. Then I want to show you another thing where on a mechanical aspect where this is a big deal. Just going to share it with you now. Yeah, so I'm designing a connecting rod, right? And if you think about a connecting rod, is positioned in between two places. Maybe one is fixed, one is moving, one is pinned. And even when you design the connecting rod, you have to take into the account of buckling, right? And in fact, what you can see here, this is from a machine design book. And you can see here, they're looking at the Rankine approach. I believe the slenderness ratios for connecting rod is within that limit. But anyway, so again, yeah, just even with a connecting rod, you have to consider buckling as well. And when they do design connecting rods, one of the things you have to look at as well. So yeah, I just thought I'd mention that. I mean, even the connecting rod itself, just looks similar to an eye profile. They do some mathematical manipulation and it kind of looks, I don't know exactly, there's some ratio you have actually between the eye section and that rod. But nevertheless, I just thought I'll mention that before we begin. Okay, so let's begin. So I have two questions which I'm going to solve. This is the first one, and I'll put up the next one as we solve. Okay, here we go. So what do we have here? We've got a shaft or column, right? There's a length of 2 meters, an outside diameter of 120 and a wall thickness of 10 millimeters. Both ends are pinned. I'm assuming we all know that's a very important keyword. E is 133 gigapascals. What I want us to determine is the critical load for Euler and the critical load for the Rankine. Okay, so these are two different approaches, basically. Normally, they will specify at this level, but yeah, I believe you all know. So before I do that, I'm just going to paste the formula for Euler in front of you, or Euler, as people call it. No? Okay, so this is the formula. I'm assuming you guys obviously went over some of the stuff. That's a formula over there, right? Really simple. So in the formula, the unknowns currently here, just in my pen here, is going to be I, because E is a material property, and then also LE, which is the equivalent length. Does anyone have an idea how we can get I and how we can get LE? So does anyone have an idea?
So I think the LE remains 2 meters because it changed ends.
Okay, cool. Is everyone familiar with what Cleo has mentioned now? That the equivalent length is still remains 2. Simpiwe, Pussy. You guys agree with that statement?
No, I'm not sure, sir. That's why
Oh,
I'm
okay,
still
fine.
listening. Yes.
Okay. So I have a recording before this one, which should have been watched, but it's fine. You know, I wasn't sure what's going on in the group. So I'll explain to you quickly where this equivalent length comes from. So I'm just gonna reshare, just share the ebook now so you can exactly see. So what is important to note is that a column can obviously be fixed or configured in different ways, right? So if I go to, what am I at now? Okay, cool. So if I go to the chapter, because this is in 6, my bad. Over here, okay, cool. Let me just scroll down. So an equivalent length, right? Again, some very important concepts which they mention is, oh, sorry, the effective length I should have used, is entirely dependent on how it's configured. In fact, what I want to say is here are the different effective lengths of the thing. So you can have both ends hinged or pinned. So they pinned over there, right? One where it's one is hinged and one is fixed. In the case where they're both fixed in the case where one end is fixed and the other one is free, right? So depending on the statement they provide you in the question, you need to now obviously get the equivalent length. So it's a simple thing. So if it's a case where Clear's mentioned is hinged to pinned, it's going to be the equivalent length will be equal to L. However, if the question had stated one end fixed, one end free, you would have to times the length given by 2. Is it clear to everyone?
Yes, sir.
Okay, cool. So that's a very important that's what I'm looking for. Concept, I guess, that you must be aware of. If you want the previous video of this one, then anyway, you can just let me know. So therefore, our LE will be equal to L. That stays the same, which in this case is going to be 2. I believe you can see my OneNote. Now we need to calculate something called the second moment of area, which is I. Does anyone have an idea of how to calculate I for a section like this? Anyone? It's in module 5, basically. I'll tell you what it is. Anyone
In
that
this one,
doesn't?
I get
Yes.
confused. I
Hmm.
get confused when it's I equals to B cube D
Okay,
over 12, and when
that's
it's
fine.
B, yes,
So
I get confused.
Busi, I is dependent on the shape of what you're dealing with. Is that clear to you? You got that?
Okay.
So what I mean by that, I was finding a table for you now, is that depending on the shape you have, your I will obviously change. So what I is, it's called the second moment of area, and what it aims to quantify is the resistance to bending. So the bigger the I value, equals resistance to bending. So the bigger the I value, basically, right, the more resistance it's going to provide to the bending. But that being said, it doesn't mean, so if you have a shape like this, right, so you have IXX, IYY. What we find is that if you bend it across the x-axis, we have a different I if you bend it over the wall compared to bending over the y-axis. So can you see that over here? That's for a rectangle shape, right? And can you see that for IX and IY, it's two different, you know what I mean? Two different formulas, basically. It's the same formula, but you know what I mean. You notice that at the circle, it's pi d4 divided by 64. Can you see that?
Yes, sir.
Yeah, so, and then obviously a triangle has its own one, depending on the axis. And of course, we have in lifts. But in this case, we're looking at a circle over here, right? Is that fair? I think you can see that over here. That's over here. You got that?
Yes, I got that, sir. But when there is thickness, and then I also get confused.
Okay, so that's fine, right? So if we can agree that pi over 64 will be d4. However, what we need to do here, remember, there's a hole in the middle here, right? There's an outside and inside diameter. So therefore, we have to remodify pi over 64. D4, big 4, big D minus small d. Now, I always get concerned when students are, let me just use the shapes here. Is there a round one here? Okay, let me see this is round. Perfect. Cool. Now use another shape over here. So I'm assuming it's roughly the center over here. Let me just configure it here. So it's quite easy to find if they give you thickness of a pipe. In fact, even when you buy piping, I'm not sure if you guys do that. They'll say certain inch pipe, whatever. But thickness, let me write it like this. The thickness is equal to big D. Is it minus small d? Big D minus small d divided by 2. Is that correct? Yes. Are you familiar with this? And so what I mean is that you can think about it like this. There's big D, right? You guys with me? You must subtract the middle one, which is green. You understand? But then we divide it by 2 because both sides should be equal on either end. Are you familiar with this over here?
Yes, sir.
Yeah. So what I'm saying to you is that, so if they give you thickness of the pipe, you can easily find that they gave us the outside, so you can easily find the inner. You know what I'm saying to you? So it'll be 2T, 2 times T minus big D, basically minus D. And we can actually find, you know what I mean? Or we can say D equals big D minus 2T. You got that? So don't get confused. So then we have big D already, and then we can find what is this? Small d using that formula. Are you with me?
Yes.
Simpiwe, Pussy, you guys with me?
Yes.
Okay. So then all we must do now is find small d, right? So our big D was given as 120, right? Is that fine? And our whole thickness was given as 10. So we just say 120 minus 2 times, what is it? 10, right? Therefore, D will be equal to 120 minus 20, which should be 100 millimeters. You guys agree with me? It's really easy. Is there any questions up until this point?
No, still fine, sir.
Okay, but you've understood what I mean. So if they give you a round section, as like a like a column like this, and they give you thickness, then obviously you want to find the, you know what I mean. It's kind of hinting. Sometimes they might give you the smaller diameter, and you need to find the bigger diameter. But what is important to note is that when you find the second moment of area, you need to use this formula over here. You see, power 64 T4 minus T4. Okay, so what I want you guys to do for me quickly is calculate I for me. Okay, so I is pi over 64. Again, it's big D to the power 4 minus small d to the power 4. And that's pi divided by pi over 64 divided by 0.12 to the power 4 minus 0.1 to the power 4. Can we get this value?
(5.27 times 10 to the negative 6
So it's 5.27.
times 10 to the negative 6.
Got you. Okay. Does everyone agree with that? Can we trust Cleo?
Yes, correct, sir.
Yes,
Okay,
it's correct.
perfect. Yeah, amazing. So what we then just do now, take that formula, and now we're going to calculate this critical load, right? So this is the load where we assume that it will buckle, right? So always say F is for the oiler, it's pi squared times E, which I believe was 133, as you can see there, times by that over there, 5.27 times 10 to the power negative 6, and then we're dividing by 2 squared. I just want to say a comment here. The reason why we're lucky, because normally with buckling, if you've done it, or struts, we normally have to look at the I with the least second moment of area. But in this case, because it's a circle, IYY and IXX is exactly the same. So IXX and IYY for a cylindrical section is the same. So can we get that buckling load quickly?
So what do you do in a case where you're not sure whether it's the same if you don't get a symmetrical drawing, basically? Do you
So
calculate
like
both
a,
Euler
a,
and
a one
Rankine?
with a one is like a bolt up section or something like that.
Like if you get a channel with
Yeah. So
I
we
beam
can.
or something.
Oh, so we're gonna do something like that next. That's the point. Yeah. So I'm doing a very basic one. Then I'm gonna do one. I think it's 2024's paper if I'm right there. We have two channels like next to each other, and then we gotta now find the second moment of area using the steel tables and
So
things like that. Yeah.
for symmetrical, it will be Ix is equal to Iyy.
Not symmetrical, just for the cylinder. You know what I mean? Like,
Oh,
so in
just
this case, are you with me? So yeah, they don't tell you. So can you see they just give you one I over here? Can you see
yes.
that? Yeah, so because both Ix and Iy was exactly the same. However, in this case, it'll be a lot different in the case of a rectangular shape. So you got to, if you have a basic rectangular shape, you got to check. You know what I mean? Which one is less over here?
Okay,
Yeah.
I see.
Yeah, just for the circle. For the circle, remember it's the same either or. Yeah. Okay, so what is that load for Euler? For Euler?
550.493 kilonewtons.
550.49.
3 kilonewtons.
Okay, perfect. So everyone happy with that? We all at least get that. I'm assuming that's correct. Yeah. That's 2 squared, eh? I wonder if you got that in. Falco and Busa, are you checking?
I've got a different answer, Seb, so I'm starting afresh.
No, but trust yourself. I mean, oh, that's -6 I do have it there. Let me work it out here. Cleo, are you checking here? And Simpiwe.
Yes, I'm checking again.
Okay. How is this? Didn't activate this license anyway. Check it. I'm just going my calculator here.
That's it's
What?
1.729 times 10 to the.
Did you square it? No.
Yes, I didn't square the pi. That's what I did.
Oh, okay. I knew something.
Yeah, that's the answer I got.
So why didn't you trust yourself?
Yes, it's
1.7 what? 1.7?
4.
294 kilonewton. The
That's
kilo or mega?
mega.
Okay,
Mega.
it's times. Okay, we can say mega newton, right? Okay, I believe you all could get that. So yeah, this is a fairly simple one, but I mean, proof of concept. So, and if you went over buckling, now there's another approach, right? And we adjust the approach depending on something called the slenderness ratio. That's if you went over. And if the slenderness ratio exceeds a certain number, I think it's, or is it between 20 and 120, you have a different approach which you must use, which is called the Rankine-Gordon approach, which essentially for short is Rankine, right? Which is over here. And the formula for that one looks like this. So when you see Rankine-Gordon, just think, or Rankine, just think, oh, okay, I need to use this formula. I don't like teaching like it, but okay, here we are. So this is the formula for Rankine-Gordon over here, right? So again here, as you can see, we're also finding another load. This is to say that's 4.2. So here we have stress, we need an area, we need to work out. And okay, let me write it like this. The data. Then we have an A, then we have an LE, then we need a K, right? So these are things we need to get that formula. So let's quickly have a look. Stress. Do they give us a stress? Yes. So they tell us the real stress of the material is 330 MPa. Okay, perfect. So that means that's 333 MPa. We need to calculate the area. That's possible, right? It's a cylindrical section with a hole inside, and that's going to be pi over 4 big D squared minus small d squared, right? Which is the same as pi r big R squared minus R squared, just by the way. I think by now you're comfortable with this formula. So can we quickly get the area, if you don't mind, before we move on? I'm assuming we can calculate that.
Can you see the diameter, sir?
I'll write it for you. Yeah, I believe it's 120 and 100. No? Small these 100, obviously in millimeters. Mr. Faku, you should be done by now. But it's clear the answer once again.
I get 3,46 times 10 to the power minus 3.
That sounds
meters.
right. Yeah. That's good. Can we corroborate his answer?
Yes, correct, sir.
Perfect. So then the next thing is A. Now this A is normally given, right? It's called a Rankine constant, and depending on the material, and if it's fixed, it will change. However, what's nice for you guys is that typically it will always be given. Can you see it over there? 1 over 7,500. Can you see that? Sometimes you might have to calculate it, but normally it's typically given. Can you see it over there? The Rankine constant. Okay? Can you guys see it over there? So it's 1 over 7,500. You see there? So depending if it's hinged,
Yes.
fixed, yeah, that will give you this value. Unless they provide the table, which I doubt. But I mean, you don't have to memorize these things. No one memorizes these things, right? And it comes from a certain place. Again, what's next is our equivalent length. As I mentioned before, depending on, you know what I mean? Depending on, what is this? How it's configured, we will determine that. So that's going to be 2 meters. It's exactly the same as the previous. You know what I mean? LE equals L. Should I write it like that rather? No? That's fine. Now you're going to find K. So if you've done your previous chapter, you have learned about something called the radius of gyration, right? And that formula looks like this. You guys know that formula? Are you guys familiar with that formula?
Yes, sir.
Okay. Anyone else?
Yes, sir.
Okay, great. So the only difference with the Rankine, again, remember, like I mentioned, the key thing here is to know is that you must use your least second moment of error. In this case, we are fortunate that we don't have to compute the least one, right? So it's basically the same thing over here. So all we must do now, we find K, and to find K, we need to root I over A. And in that case, we computed I, right? I was 5.27. My hands wet. No, sorry. It's on my tablet. Okay, 5.27 times 10 to negative 6. And then we're going to divide all of that by, obviously, we're going to divide it by the area which Mr. Falco has calculated, which is 3.46 times 10 to negative 3. That's good. Okay, are we happy with that? Let's get that. Okay. And by the way, the unit of this is millimeters. It should be. Just never mind. Okay, cool. So let's quickly get K's answer. Millimeters or meters? I mean, yeah.
So for the stress, this formula,
Yeah.
do we use the yield stress, or because I don't see it's given the factor of safety to
Yeah. So
divide?
no, sure. So you have to use the yield, but if they give you a factor of safety, obviously you must divide. But you normally notice those numbers, like they give you that the stress is like normally like 600, 900, then you must obviously divide. So this would be, yeah. Unless they specify factor of safety, then you probably won't divide it all.
Okay.
Yeah, so it's typically clear. Let me just check the one we're going to do now while you guys are calculating it. I think it has a factor of safety. Let me just check. Yeah, it's last December 2024. I'll show it to you. Does it have factor safety? No, it doesn't. But yeah, does its job. Okay. Mr. Falco, what did you get?
I got 0.039.
Okay. Then you guys 0.039. Basically nearly 40 millimeters. Someone is joining. Oh,
That's right.
okay. Is that right? Okay, Cleo says right, so it must be right. So let's move on. Once that is done, it's a plug and play game, right? I hope you guys can see that. So hopefully you'll get a question like this in the exam. So F equals 3 times 10 to the power 6. You times the area. Area is 3.46 times 10 to the negative 3. We divide that by 1 plus 1 over 7,500. Equivalent length was 2. Basically, this over here is your slenderness ratio. 2 divided by 0.039 squared. And then you get your buckling formula, your Rankine buckling formula. Just gonna get the other questions along. There's 14 marks, right? That's 14% of the paper in the pocket. Akif, welcome.
Hi there, sir.
Now, when you start a new question answer, don't worry. Yeah. So what do we get for that F? So what do you guys get?
So I got my answer in Newton's 853.364.
853.6
364.
364. Okay, it's okay, cool. There we go. Colleagues, could you get the same answer?
So it's in Newton's on my end.
Oh, just newtons. So it's quite
Yes.
small, like that. Like
Yes.
853 newtons. That's
That's yeah.
so,
It looks
suspicious.
suspicious. But okay, let me redo it again.
Yeah. So that's power 6. That's power negative 3, eh? And just check your squaring because you don't like to square, it seems. Mr. Falco and Busi, what do you guys get? And Busi, please trust your answer, eh? I mean, I could be, but I mean, it's so small. Yeah.
I got 1,132 times 10 to
No,
the power
it
6.
cannot be that. No. No. That's 800 and something for sure. But I'm not sure if it's exactly so small. Must I let you guys how to use the calculator as well? Is this where we are? Guys, remember the promises you made to yourself and your family. Yes. 0.0.
No, it's 853.364 kilonewtons.
It's all the decimal places. Yeah, it's kilonewtons, right?
Yes.
Yes, yes. I get 853.2035. What did you say? 634. Is yours 634? Is it the same basically? What's this kilonewtons?
It's four, so it's the same, just
Okay.
kilo.
So where do you make your
But
mistake?
it's not 636, it's 364 only.
Okay. 364.
After the decimal place.
Okay, got it. Like that. 6364.
Yes.
I got a
No,
different answer.
it's 364, so 853.36
Okay, wait.
kilonewtons.
853 point.
364.
Oh, okay. Okay, thank you very much.
Yes.
Can we all agree with that one? I got a different one. 5.27. Other colleagues, can you please confirm? 527, then 3.46. Okay. Are you guys still there? Oh man. 3.46. Okay, cool. It's fine. Okay, I'm assuming everyone has got that answer. Lucy, Akif, you guys get it? Is there any questions before we move on? I'm just going to place this question as well.
Yes,
No
got it.
questions.
Okay. Yes, do you have? No questions. Okay. All right. This is December 2024. Last year's paper. Okay. So this one, what's nice about it, what they typically do with these type of questions, there's two ways they'll ask these questions. This is the standard over here, where they'll ask you the second moment of area. And then from this part here, they'll either can ask you buckling. I call it buckling, the column and struts, module 6, or they can ask you a bending type question. I'm sure you've picked that up if you've engaged with the video and you've practiced, right? So in this case, it's a buckling question, obviously, right? Because that's what's important. I believe, Cleo, you asked something like this, where you have two different sections now, right? It was not symmetrical. Or they give you a steel section. Yeah. Um, yeah. So this is kind of symmetrical still, but anyway, two different steel sections. Anyway. So here we have a strut, right? Its length is 5 meters, and there's two sections, 280 by 95 by 41.8 kilogram per meter channels, right? I'm not sure if they actually both struts like this, but anyway, okay, cool. If you could imagine this, imagine something like that, like one channel like that. You know what I mean? And okay, obviously my sketch is a bit sus, but okay, it's fine. And my other channels like that. Can you see it there? Right? We're not sure what it's supporting. There could be something obviously on top of this. We don't know. There could even be 4 of these things. The question is here, determine the second moment of area, what XXX, what YYY, the slenderness ratio, which we talked about, and then also the Rankine constant. So again, yeah, they're basically telling you, oh, okay, right? You're gonna want to be using this equation over here or model. Let me just copy this thing over here. Okay, but let's quickly see what we have. We have the stress given, we've got the load. In this case, they give us a buckling load, but now we need to calculate I. Both hinged again, both hinged, huh? Both hinged, okay, whatever. That's obviously tells us our effective length. And then we have K, we must calculate. And then obviously, yeah, that's going to fall into the slenderness ratio. But anyway, now we need to calculate I, right? Because you know that K, where the gyration is equal to I minimum divided by area. So how do we get these things now? Okay. So colleagues, are you familiar with the steel tables? Musi, Akif. You guys touched the steel tables yet? Yes or
Yes,
no?
sir.
Okay. Akif, have you touched it, Mr. Faku? Video?
Yes, sir.
Okay, cool.
Yes.
So obviously with this, it will be provided. And what you have to do here is go look at the steel table, right? And get these properties. So what I'll do now, I'll go find that and I'll paste it there for us so we can actually take the, that's what I'm looking for, the respective property from it, if I can find it here. Okay, short answers over here. Here we go. It's a channel, right? Okay. What's it again? Let me just see here. 280 by whatever. Okay. 280. Why am I not seeing it here? I'm just checking for the channel, guys. Just give me a second. I'm just gonna rotate this quickly. 280 by what's it? 95, right? I'm not seeing it in my steel table. Can you check your steel table? It's 280 by 95. Let's check the steel table quickly. I'm sure the section exists, but let's quickly get one. Some of you guys can see it though. Unless they made a hectic mistake in the
Yes,
you see it?
Yes, sir.
yes, sir.
So where is it? Tell me. I can't see it. 280 or
I'm
230?
using
Like table, what is it? Like table 4, 5? I'm not seeing it, man. This is from the book now anyway.
So I'm using the weekends textbook.
Okay. Just check
From page
weekends.
95.
Okay. And not the Detroit one.
No, I'm using weekends.
Okay, cool. Let's quickly look at let me see if I can find. I have the old copy of weekends. I wonder if it's there. And by the way, steel tables are supposed to be standardized, meaning all structural engineers use exactly the same steel tables. It's standard across the world basically. The sections don't change unless you have to make up your own. See a bit concrete. Okay, I have the weekends open here now. It's just loading. Give me a second. If you have it, then you can just so long share your values. Let me just rotate quickly. Okay, cool.
So looking
Yeah.
at I about the XX axis.
Can you repeat that? I think I got it. 280 by 95. I got it. That's the weekends one, yeah. Just give me a second. I just want to rotate this, man.
Okay.
And okay, cool. I got it. I'm not sure why is it not rotating it soon. Just give me a second. All right, guys, can you see that? That's my steel table. Why can't I rotate it? Yeah, rotate.
So
There
I
you
was
go.
asking if we could use the if we should look at the I value of the XX axis.
Yeah, I'm gonna get to that now. Sorry, just give me a second. I'm just trying to rotate.
Okay.
Yeah, there we go. Okay, cool. So that's our table. And in question, the steel section we're using is obviously this guy over here. Let me just draw a line. We all can see it. Cool. That's that one there, right? So I just highlight everything so we can see. Okay. That one there. We're all content with this, eh? So now reverting to this here, so we have to look at the way it's obviously configured. And I think that's what Cleo's asking here, that it's, can you see it's based like this, right? So we have to use for, we're going to have to do IYY and IXX and check which one is the least. That's what we're going to do. But anyway, the first point is 6.1, and they want it in the x-axis. Can we all agree this is the x-axis, right? That's the y. So in this case, all we have to basically do now, which is going right through here, like exactly in the middle. So all we have to do is look at what our IXX is. In this case, it's going to be that one there, right? 62.76. So colleagues, are we happy with that? I'm not done, but can we all see that there? Am I seeing the right thing?
Yes.
Yeah. Anyone else? 62.76, right? Are we content with that?
Yes, sir.
Okay, but obviously, because we have two sections, we must times it by 2, right? That's fine. So it's 62 point. And some just tell me again. Was it 7 something?
7.6.
7.6, right? And the total IXX will just simply just be 2 times that value over here. Right? There's no parallel axis theorem here. It's going right through that center over there. And that should give you 125, right? It's 0.7 there. 125 point something. We're content with that. 0.52 meters for. So we're happy with that. 2 marks, right? Easy. Normally for buckling, they never make the IYY and IXX too difficult. But again, it's possible that they can mess you around. Oh, yeah, they can challenge you a bit more. So we're happy with this. Timesing by 2, but it's 2 sections and it's going exactly through that. Okay.
Yes, sir.
Well, can we move on? Can we do IYY now?
Yes,
Yes.
sir.
Okay, cool. So IYY, remember this now here is our center, right? So let me just be really obvious here. So now to find IYY, we can't just simply take IYY from this because IYY here, right? We can actually see IYY. How can I go in now? Right? Or zoom in, zoom out. Okay, anyway. IYY is over there, right? Can you see there? It's not at the end, it's a distance away. Can you guys see that? The center of the channel somewhere there. I hope everyone can see that. So what I'm saying is, if we revert back to our sketch over here, IYY is somewhere here, right? Like that. You see? So now the parallel axis theorem, obviously it's also on the other side as well. What we're going to have to do now is, if you remember, you saw a formula like this, which is let me write it here, I equals IXX plus A times some distance squared. Have you seen this before? Something like that?
Yep.
Yes,
You
sir.
see this? Yeah. So this is used when the section is away from the center over here. So all you have to do now is find the distance from here to there. You understand? So what we're going to do, we'll take IYY as is, right? And then we have to say plus the area of the section times that distance. This would be called h, right? There's different ways to call this, obviously. People call it different things, but I hope you get the idea. So now we need to find what is the distance from there, from here. Just make this big again. From here to there, right? Do you have any idea how you can find it? It's fairly easy, I think. Be careful in saying that.
Will it be divided by 2, sir?
No, because they give you AY. Do you know what this AY is for? That value here? It's a good guess. What's AY for? AY tells you the center of this particular shape over here. You see there? So then
Okay.
B, yeah, so it's going to actually be, so you kind of right. It's actually going to be B, right? Minus AY. Is that clear? So let me just sketch our own one here. No, let me just be a bit dramatic now. So B is this distance here, right? From here to here. And okay. And obviously AY is somewhere there, right? Are you with me, colleagues? Got that, no? AY is okay, that's not AY is here, from here to here somewhere. You see? So we need to find that distance from here to there, right? It's going to be fairly simple. We can say our H is going to be equal to, what is B in this case? 95, right? 95. And that's B, by the way, as you can see there. 95 minus this over here. So 95 minus 25.30. And the reason why we're doing this is because it's not in the center of our assembly. So now we have to use a parallel axis theorem. Is that clear to everyone? I hope so. If not, please tell me.
No,
So what is
sir.
up? Okay, so what's bothering you?
I don't know. I'm used to just working out like B divided by 2.
Yeah, so
Because it's like then that's obviously the centroid of the channel.
it's not, that's the thing. It's not exactly. The center is not B divided by 2. It's not an I-beam. It's a channel. You know what I'm trying to say? It's a different type. Yeah. Because it seems so simple, but if you orientate the channel like this, like where's the center? Is the center, it's here somewhere. You know what I'm saying to you? It's not actually B divided by 2. You can only do that if it's a perfect, you know what I mean? Your logic is right if you have a perfect triangle. You see what I'm saying to you? I mean, it's triangle, rectangle. But so imagine you have a perfect rectangle, but then what happens if you remove some, you know what I mean? Some, what is the word I'm looking for? Some of the material in the middle. You can't tell me that the center of gravity is exactly the same, but it has to change somewhere. You know what I mean? Because this piece is missing now. So it has to be positioned somewhere. You get the idea. So with channel, always be careful of the AY. That tells you where the center is.
Okay.
Anyone else? Yeah. That's what's given there as well. Akif, Simpiwe. Okay. So let's quickly work out that H. 95.3, 95 minus 25.3. So your answer 69.7. You know that 51% for the subject is a distinction, right? You guys are aware of that. I'll be content with this.
So is the H the same or same thing that I call R?
Yeah, that's correct. Yeah, it's the same thing. Just the distance. I think maybe use R for the vertical. Yeah. As long as you understand. Yeah. Is everyone happy with this here? The 69.7. Because everyone went quiet here, besides Cleo. Nevertheless, so we got the answer of what again? 69.7. So now for us to find our IYY, it's going to be, how do they write it here? Which IYY total is equal to 2, obviously. The reason why I'm saying 2 because it's the same on either in IYY plus A And we're going to call it R in this case, right? R or H doesn't make a difference, right? So we can say R1. I think R they use for the horizontal and H they use for the vertical. Same thing. So 2 times. So IYY, we must still check our section. And that case, IYY was 3.982. Can you see it there? Am I right? Yeah. So that there? Can you guys see it? That's I.
Yes, sir.
Yeah.
Yes, sir.
You put in there 3.982 times 10 to the power negative 6 plus the area. The area is given as 5.342 negative 3.342. Okay. 5.342 negative 3. And that R, sorry, my bad. I made a mistake here. That R is not outside. R is here. I mean, the square is here. And then obviously we found it to be 69.7. All right. So, okay. So you just say that times 0.0697 and we squared it. Close the bracket to times by 2. So can we get that IYY? And again, we're going to have to compare what is more IXX or IYY. That's going to be important in the next part of the thing. I'll keep left. Can we get an IYY?
I got 51,904.
Okay, 59,104.
904.
So we said 59, comma?
904.
Okay, 904. That seems quite close enough, yeah. Meters 4. 59,904. Colleagues, you agree with that one?
Not 59, say 51. 51.
51.
Yes.
That's not correct. You got to check again. Remember, this is negative 3 here, no? I'm using a thick pen here. Just make it thin. It's negative 3. That's squared. That's negative 6. Anyone's got the answer?
I got 59,867 times 10 to the negative 6.
Yeah, that sounds accurate. 59,867. Let's see. Can anyone else corroborate that? 59,867, eh? 867.
So,
Am I right? 867.
yes, sir. 867.
The Falco is still there?
Yes.
Okay. Stay, the materials can give you a flu now. It can increase the blood pressure. I'm just letting you know. Could we all get that? Ah. Okay, cool. Okay, so let's move on. Right, so that's definitely correct. So now, very important here, between these two values, right? It means that in this column is most likely to buckle, right, on the y axis. Meaning, where's my y? My y is like this in this case, right? So it's gonna buckle y. You know what I mean? Not on the x. So we've got that. Now they want something called the slenderness ratio. Slenderness ratio is that part, this S is R over K, is exactly the same as, let me just zoom out again, zoom out to zoom in. Yeah, that's exactly the same from that formula over there. So you notice in the Rankine Gordon formula, the slenderness ratio is over there. So we needed to calculate this anyway, right? So all we must basically do now is find this, right? But SR is equal to LE over K. And remember in the previous question, K was I min, right? Divided by the area. But what I should have mentioned, our area as well, we must be careful. I think our area we must times by 2, eh? Am I right? Or do we find the total area? Yeah. Am I right? I think so. Anyway, I hope so. Okay, so obviously our L is easy. That's the question said is what? Both ends are hinged, right? So it's exactly like the previous question. So let me just be deliberate again and show you the table so you can actually see it. Okay. Cool. I'll just use this. I'll use the image again so you can see. Place it over here. So again, just to recap, both ends hinged, LE equals L. If it's one end hinged, one end fixed, right? It'll look like we have to times that by the effective limits. In this case, it's going to be the same. So in this case, our length was 5, right? So that's fine. So we know L is 5. So can we actually get our, what is it called again? Our radius of gyration. So okay, just calculate it over here. So it'll be I min over the area. Just
So
thinking,
we use sorry,
yes,
we use the one with the weakest axis again for
that
this.
is correct. Yeah. So between the two, this one is weaker, right? They're both -6, so that one's 59. That's a smaller one. Just thinking about the area. For the area, you must times by 2 as well. You must consider the whole area. I hope I'm right anyway. Should be. So I min is 59.864, 867 times -6, power 6, right? And then we're going to say 2 times the total area in this case, because remember, we have to look at the whole area of the thing. And we did times it by 2 here, which is a 5.3 something. 342. Let me just 342 times 10 to the -3. Okay. And once you've done that, I want you to calculate the slenderness ratio for me. I'll give you guys 2 minutes to do that quickly.
So I got 66.794.
All right, colleagues, did we get it? Leo, Busi, Simpiwe, Akif. What did we get?
66.794.
Is it correct? 66.794. I hope that's correct.
I got a different answer.
What is your answer?
I got 74.85 times 10 to
74.8. You're the two of you guys and your answers, man. It's rough,
not
man.
for this one.
Oh,
For
so sorry, I was on the slenderness ratio already.
Oh, okay. So this
Yeah.
one, yeah. The 74.
Yes, that's correct.
Okay. Okay. Oh, finally. I'm just thinking now. Just want to check something here. And you can just check the slenderness ratio. I just want to check something. Where's our section again? No. Definitely. Yeah, we have to use a total area, man. I don't know why my brain is telling me something. Yeah, you have to use a total area. You can't just use one. Yeah. I've learned to trust myself. Okay, so if that's done, I'll leave it. I'll end it here, and you obviously can check the past paper for 6.4, but 6.4 is fairly easy. I like you guys to do it, and all we basically do is take all our individual parts over here, and we're just gonna have to solve for that A, right? So F was given here as 200 kilonewtons. The allowable stress is 160. Maybe you should just do it. That's 160 megapascals. Our area, which I believe we must still say the whole area. I'm still feeling quite funny about the area, because do we use 2 times 2? Do we use, you know what I'm saying to you? We have to consider the whole area because it's the whole column itself. So that's still bothering me now. I'm just not sure about that. And then obviously 1 plus A, which we're looking for. And then we have L over E, which is the slenderness ratio. In this case, I think Cleo's got 66.794 squared. And the only unknown is basically A. All right. Is there any questions, colleagues, before we conclude? That area is still bothering me, but anyway, yeah. I'm pretty sure I'm right.
So
Yeah,
are
any
we
questions? Hey?
Are we given A?
Yes, we are given A. We took A here. It's coming from the table, Pussy. Where is it now? There's A. Yeah, you see there, 5.342.
Okay, the one for area.
That's for area. That's A. A is area. There you go. Can you see that, Busi?
Yes,
Can you
I
not
can
see
see.
it? Yeah, there's it. 5.32. There's it. See that? I use that same thing
You
there.
use the same
Yes.
thing
Excuse
on
me?
that. You use the same A.
Same A. But you use the same A here as well. Can you see the same A? Can you see that?
Yes, sir.
And then the same A again. This there on top. That's the A. Oh, you're talking about this small A, the small one, the small one we're working out.
Yes.
We are finding that A.
How do you work out that A, sir? Because I got confused in the other question paper I was doing.
Okay, but I mean it's just simple maths here, right? We're just timesing 200 over here. Cross multiply if you want. 1 plus A times 66.794 squared. Right? Are you count? Can you see what I'm doing here? Right? That's multiplied there. We have 160 times power 6. Just want to confirm it is 160. That's your yield. And then times the total area. I'm pretty sure that's the case. -3. And obviously you want to solve for this, then this is going to be quite simple. It's going to be 1 plus A 66.794 squared. That's 160 times 10 power 6 times 2 times 5.342 times -3. And we divide this by 200. What about that? Well, that only doing the n is carry over the 1 as well. The 1 can come over. Are you with me, Boosie?
Yes, sir.
Yeah, and then the 1 is there. Obviously, you can also divide by the 66.794 again, which is over here. No, I cannot just do that. So whatever you find, what is this value again? Let me just undo that. It's 200. Oh, yeah. So you have to divide all of this by 66.794 squared, right? And obviously, because you have, and that'll be A. Yeah, there's no squared on the A. So just delete that. And that'll be A. It's just maths, basically. You see that? Normally, they don't ask you to find A. I mean, they normally give you A, but that is what it is in this case.
And when do we use this one with A over 4?
A over 4. What is that?
Yes, it's here on the formula sheet.
Let
The
me have a
F is
look.
plus times area over 1 plus A over 4.
A over 4.
Brackets LE over K squared.
Oh, I see. Yeah, so let me just open it up. So I think what I'll do, I'll show it to you now. So I'll just, you're referring to these ones, no? I'll take it now. So that's A. So don't get confused. Just use the ones that I've shown you, right? So the only difference between the two, if you look at it, right? Can you see here's LE, this one here, and this one here. Can you see the difference here? Let's look at these two here.
Yes.
Yeah. The one has effective length, the other one doesn't have effective length. You see there? One has effective length, the other one doesn't have effective length. You see? And if I were to unpack that, so obviously you want to use the one with effective length. You know what I'm saying to you? That's just, I don't know why they gave you the other one. I really have no idea why. I'm just trying to see if I can find something to assist you. Yeah, there's no other reason why. Just use, there is a straight line formula as well, which is another approach for buckling. Yeah, you just focus on the one with the effective length. That's it. You know what I mean? Don't worry about the rest. It does the same job. Are you with me, Boosie? Just understand the effective length. Yeah.
Right.
Maybe anyone else has a comment on that one? You shouldn't.
So I just know what the unit is for the A. And when do you make it 1 over A?
1 over A. So the unit, I don't think it has a unit. It probably possibly does have a unit. I'm gonna just quickly check the thing now. And when you find A, if you use a calculator, you can actually put it as a fraction for you. I don't know if you know what I mean. Then you will set 1 over something. So you don't have to make it 1 over something. Because 1 over a particular value is, you know what I mean? So you get a decimal place, and then you just click like the S to D function on your calculator, and it will make it into a fraction. But it does have a unit. The unit's probably going to be the same. I have to look at the actual formula and see it myself. But normally it's a constant, man. Maybe I don't think it could be unitless as far as I'm concerned. Let me just think about it. It's a stress divided by a length. It could be a unit, but it's a constant, so there's no unit, right? And I'm saying that very carefully. Yeah, it's a constant, so no unit. As it says, it's the Rankine constant. You know what I mean? Yeah.
Yes.
Yeah. Is there any other questions before we conclude?
Sorry, sir. Have you done
Hmm.
framework yet?
No,
Oh,
I'm not planning to do frameworks.
okay.
Hmm.
Okay, no
It
problem.
wasn't enough time. I never get to frameworks anyway. So,
Okay.
but yeah. I normally end of this module. I think as I teach, like, probably teach next trimester, then I'll try to get some decent stuff, or at least to stuff remotely, and then send it on frameworks, because it's just the syllabus is just so tight, man. So what I suggest, don't worry about these ones. Yeah, it's of no benefit at this point. I don't want to unpack exactly what's going on here. It's critical time now. Is there any other questions? None. Okay. Okay, guys.
No, sir.
Yeah. And again, the way I recommend when you approach the exam, just make sure know what you know, man. You know what I mean? Don't if you don't know something, don't prioritize it. Because I believe your pass marks only 40. And obviously you guys want like a 50%. But let me just quickly show you something here. And obviously the frameworks, there is easy marks to get, and that's finding moments. But I'm gonna just put this up here in conclusion, and so you can actually see. So like structure your preparation. Yeah, as you can see, can you see what's important over here? See what I'm saying to you? So toggle your preparation in line with this. It's roughly within these parameters. Am I clear, colleagues?
Yes,
You
sir.
don't want to spend too long on something which is not going to provide movement. I mean, these are arguably easy marks. That one, temperature, strain can be a bit of a problem for some people. Fin is also fine if you know your mores as well. Simple bending and struts, these two talk nicely to each other. And then shafts is also I think it's quite easy. And then mostly odds for the hollow, you're replacing a solid shaft for a hollow shaft. I've seen it too many times. So then frameworks, you can get a few percent from this just by finding the moments at least. So yeah, it's a tough subject, I know, but anyway. But quality over quantity. That's my recommendation. All right, guys.
So
Yes.
sorry, I heard that they use 40%, I think, of the class mark of what we've qualified was to get into the exam. Is that correct?
Yes, that's correct. Yeah. Yes, that's correct. Let me just quickly. I mean, I don't want to. Okay, let me stop recording here. I don't know. I don't want to show mark. Okay, let me just quickly show you something. So I'll use. I'm gonna open up a spreadsheet now.